Hello, everybody. Hopefully, you're doing well. We're gonna continue with chapter P, that we call prerequisites of fundamental concept of algebra. In the first section, if you don't have a chance to look at it yet, I would strongly advise you to look for this video and watch algebraic expressions, mathematical models, and real numbers, where we review all type of algebraic expressions, real numbers, and try to translate into mathematical model English sentence. In this video, we're going to take a closer look on exponents and scientific notation. As you know, there are so many big giant numbers that we cannot just write as a regular number. For example, the US debt, right? It's a big giant number. We call it trillions. Thousands have 4 digits, and you know, millions have 7 digits, billions have 10 digits, and then trillions, it's after that, right? So those type of numbers we're gonna use like scientific notation to do it. In order to use scientific notation, you need to understand also exponents, expressions containing exponents. So we're going to use the product rule, use the quotient rule, use the zero exponent rule, use the negative exponent rule, use the power rule, find the power of a product, find the power of a quotient, simplify expressions, exponential expressions, and at the end, we can, you know, use scientific notation, right? Okay, let's try to see. When you multiply, usually what happened, we have seen that exponents are used to indicate repeated multiplications, right? When you multiply exponent expressions with the same base, add the exponent. So use this sum as the exponent of the common base. So what you need to do, right? If you consider the multiplication of two exponential expressions, such as you see, for example, if I take x power 5 times x power 7, all right? So we are multiplying the factors, I mean the bases, with an exponent and another basis. But because the bases are the same, what we can do is keep the same base, and we add the exponent. So that's why we said this formula right there is the product rule. When you have the same base, what you do, you keep the base and you multiply the exponents. If I have y power 2 times y, remember, if because it says y is usually power 1 if you don't put in something bigger than 1. So you're gonna have y equal 2 plus 1, so is y to the third power. But you need to make sure you see that the bases are the same. I'm not what let's suppose you see y power 5 times x power 7. What would that be? You cannot add the exponents because the bases are not the same. So that's what you're going to need to understand here. So this one stay as is. But when you divide exponential expressions with the same non-zero base, you subtract the exponent in the denominator from the exponent in the numerator. So for example, if I have x power 6 over x power 2, because we have xx, we're gonna subtract the exponent 6 minus 2, so x is power 4. But what if you have x power 5 over y power 2? Nothing happened. It's gonna only be x power 5 over y power 2 because the bases are not the same, so you cannot change it. So that's the uh, product and rule and quotient rules. I'm hoping you got this one correct because we're gonna do some multiplication first. Let's suppose look at these examples for multiplication. Well, if you see something different, let's multiply this. So if you have 3 you know, power 4 times 3 power 2, right? What would that be? So because the bases are the same, you can do 3 power 4 plus 2 is 3 power 6. So you grab your calculator and you do 3 power 6, all right? So I believe that should give you maybe 729. Or you can see it the other way also. Suppose you have 3 power 4 is like 3 times 3 times 3 times 3. And 3 power 2 is 3 times 3. So you see, you have 6 threes here. So because you count the number of factors you have, you can say, you know, it's like you have 81 times 9. What is 81? You can only do that multiplication. 81 times 9, it gives you 729. So the answer would be the same, right? But that's for real numbers. What if it is not real number? What if it is variables? So the first thing is to combine the like terms. So we're gonna combine the constant together. So that means we're gonna take the constant and we multiply them together. For example, 4 times 10, right? We're going to multiply the like terms x together. So I mean x power 3 times x power 2, because it's multiplication, we can do it that way. And we're gonna do y power 4 times y power 6. Now 4 times 8 is 40. 4 times 10 is 40. Now you see for x power 3 plus 2 times y power 4 plus 6. So we have 40 x to the 5th, y to the 10. Okay, so if you're okay with that one, and for divisions, you see product rule or quotient rule. If we call it quotient rule, look at this one for quotient rule. If we have, for example, 3 power 6 over 3 power 2, we can say it's 3 power 6 minus 2 is 3 power 4. You know, 3 power 4 is 3 times 3 times 3 times 3. That gives you 81, right? So that's for constant. But what if you have an algebraic expressions like this one? So this is an algebraic expressions, right? So for the algebraic expressions, what you need to do, I'm going to try to see if I can move that expressions to the front. You know what? Is it possible to put it? Okay, right there. Okay, that's good. We're gonna put it there. Now, what you can see, focus on the constant first, real numbers first. You see, you can say 27 over 3 times x over 14 x over 3 times y over 8 y over 5. So 27 over 3 give you 9, if you remember, that's give you 9. Remember, x power 14 minus 3 times y power 8 minus 5. So it's give you 9 x to the 11 times y to the third. Right? You okay with that? Great. If you're okay with that, then I'm okay with it. Okay. So that's how we start with, you know, we covered these two, product rule and quotient rule. Very important. Now, let's see some other rules. For example, zero. If we do the zero as an exponent, or you call it the zero exponent, a non-zero base can be raised to a 0 power, any non-zero base. For example, you can have 5 power 0, okay? The quotient rule can be used to help determine what 0 as an exponent should be. So if we consider, you know, something like Quotient rules can be 5 power 6 over 5 power 6. Do you know it's 5 power 6 minus 6? 5 power 0 is what? All right. So what we said, the rule says for us, any non-zero number power 0 is equal to 1. So any non-zero number. So if b is any real number other than 0, then b power 0 is 1. For example, 10 power 0 is 1. 156 power 0 is 1. All right? Any non-zero number. So if we have negative 6 power 0 is 1. So any non-zero number would give you 0. All right? Sorry, I think I said negative 6. Remember, this one can be written as negative 1, but you can do negative 6 like this, power 0 is positive 1. So if it's only negative without parentheses for 6 power 0, then it's not 1. Okay, if you got that, how about with the negative integers as exponents? So we know 0 as an exponent. We have the negative integer as an exponent. It's like the negative exponent rule. A non-zero base can be raised to a negative power. So there is no problem for your exponents to be negative. So in this case, if b is any real number other than 0, and n is a natural number, so you know if you have a b power negative n, it's to make the exponent positive, you just flip it. Because remember 2 power, let's put the positive first to see. We're gonna have 2 power 3 is 2 times 2 times 2, that's 8. But 2 power negative 3, if you try to do it in your calculator, that is not a very scientific calculator, it might give you error, right? So if you do power 3, it would give you 0 if in an error if your calculator is not scientific. But with scientific calculator, possibly it can give it to you. But what you need to do is flip it. If it's the exponent, negative exponent is in the numerator, you need to jump it to the denominator. If it's in the denominator, jump it to the numerator. So that would be 1 over 2 power positive 3. So it's 1 over 8. Okay. All right. If you got that correct, how about we try some examples? For example, use the negative exponent rule to write each expressions with the positive exponent. All right. So what we can do with that one, if they give us this one, we know is 1 over 5 power 2 positive. Okay. We make sure that we write it 1 over 25. If you have negative 3 power negative 3, we need to do 1 over negative 3 power 3. Okay. So when remember negative 3 power 3, negative 3 power 3, that gives you negative 3 times negative 3 times negative 3. 3 negative is negative, so negative 27. So we're going to have 1 over negative 27. And if you put the fraction and negative in front of the fraction bar, it gives you 1 over 27. The same, I'm gonna just keep enough space for these two. Let's do another one. If we have something like, let's try another one. Let's go 1 over 4 power negative 2. You see, that negative is in the denominator for the exponent. So we need to flip it to the numerator. So it's like we're gonna jump it. So it's gonna be 4 power 2. We make it positive. That would be 16. Okay. Now let's suppose we have an expressions containing some variables like x and y. So first of all, the 3 remain the 3. The y power is 4, we mean y power 4. But because the negative exponent is only for the 6, for the x, so the x would jump to the bottom. So we make it positive. Okay? So we make it positive then. Okay? That's extremely important that we do that. Okay? Now, when an exponential expression is raised to a power, multiply the exponent, okay? Please place the product of the exponent on the base and remove the parentheses. So we call that power rule. Power of a power, we keep the base, we multiply the exponents. For example, if I have x power 2 power 3, all I need to do, multiply the exponents. So with the same base, keep the base and multiply the exponent for power. Power of a power, we multiply the exponent. The products to power rule for exponent, when a product is raised to a power, raise each factor to that power, right? So you need to do you need to distribute. For example, 2x cubed y squared power 3. First of all, we're going to have 2 power 3 x cubed power 3 y squared power 3. So that make it 8. Power of a power 3 times 3 is 9, x power 9, y 2 times 3 is 6. So power of a power, we multiply the exponents, okay? But first of all, we need to distribute, okay? So remember, the exponents, when you have a parenthesis, you need to distribute the exponent to every member inside of the parenthesis, okay? Now, look at that one. Power over power, what you do? Yay, that would be 3 power 3 times 2 is 3 power 6. Now, you grab your calculator because in this class, you can use calculator. If you do 3 power 6, it's gonna give you 729 because we tried that before. Now, if you have a variables, the b stay b, remember it's -3 times -4. 2 negative in multiplication is what? +12. And that's the exponent. That's what I just did in the previous examples on the other slides. So now these exponents need to be distributed not only to the -4, we also need to do it for the x. So we're gonna have -4 power 3 times x power 3. So that's give us what is -4 power 3. Remember, if you raise 4 to power 3, 3 negative become positive. Thank you. Because any times the exponent is odd, for if the base is negative, the answer is negative, right? So power 3, power 5, power 7, etc. So we're gonna have -64 x to the 3rd power, okay? And that will be the answer for that expression. Now it's different when you have many different terms, you know, to deal with, but if it's that simple, then you can do it, okay? Now, I wish you could be here to ask more questions about that, but you know what? We're gonna continue talking about quotients to power rule for exponents. So what we mean by that, when a quotient is raised to a power, raise the numerator to that power and divide by the denominator to that same power. Now, look at the difference. When you have the same base with exponent, we subtract the exponent. Now, when we have different base, like you see, you have x over y power 6, you're gonna have x power 6 and y power 6. You distribute that exponent. But it could be something different, but we're gonna see that. Pay attention, especially if b is a non-zero real number, right? So a over b power n is a power n over b power n. So when a quotient is raised to a power, raise the numerator to that power and divide by the denominator, right? So we can have so many big expressions probably we can use after. You would see, let's suppose you have 6x y cubed over 2x to the fifth y cubed power 2, right? First of all, you make sure you give the numerator, you distribute the exponent with the numerator by itself and the denominator by itself. Now, from there, you're going to give each of them their own exponents, like 6 power 2, y power 2, x power 2, y square power 2. That's for the top one. The bottom one would be 2 power 2, x5 power 2, y3 power 2. Now, when you simplify, it's going to give you 6 power 2 is 36, x squared, y to the fourth, over 4, x to the 10, y to the 6. Remember, our goal here is, I just take a random examples, right? Examples. Let me put examples. Remember, I use examples a lot to explain. 36 divided by 4 would give you 9. And then look what happened. If you do x 2 minus 10, y 4 minus 6, right? Because you need to subtract the exponent when the bases are the same, because we collect like terms. We're gonna have 9x power negative 8, y power negative 2. But because you cannot leave it like this, it must be positive. It's going to give you 9 over x power 8, y power 2, positive. Well, use that example because I said we're gonna have a chance to do so many. Pause the video if you want to understand better how I get to that positive answer at the end, because at the end, the answer is 9 over x power 8 and y power 2. As we said, you cannot express your answer in this negative exponent. So you need to make sure you flip it to the denominator if the numerator in the exponent if the exponent in the numerator is negative, you flip it to the denominator, or you can do it vice versa. All right, so look at these examples. First of all, because the both bases are different, so we're gonna, the negative, you can decide to put the negative anywhere you want. Do you want, because the negative would be either with a y or with the 2. So if I decide to put negative 2 power 5 over y power 5, you see I give each of them their own. If you do negative 2 power 5, that means multiply negative 2 by itself 5 times. I'm pretty sure you know it's gonna be negative 32 over y power 5. If you want, put the negative in front of the fraction bar, y power 5. The same, we realize in this one, if we do x power 5, 3 over 3 power 3, x power 15 over 27. So because 3 power 3 is 27. Questions? No, you're not here to answer the questions. At this point, we only need to expect for you to be here. But okay, let me address another issues. For the algebraic expressions, you know, we covered the difference between algebraic expressions and equations. Equations is a statement that two algebraic expressions are equal. For the algebraic expressions, the best you can do is to combine like terms, you know, evaluating for a certain value of the variable, all right? But simplification, when we combine like terms, we try to find terms that we can cancel out or combine together. So we call this process simplification. So properties of exponents are used to simplify exponential expressions. So an exponential expressions is simplified when no parentheses appear, no powers are raised to powers, each base occurs only once, no negative or zero exponents appear. So if you see all of this, then you said, well, that's true. Remember, we covered all those type of exponents. We said if you see a power m over a power n, it gives you a power m minus n. If you see a power m times a power n, you add the exponent. That's what we just covered. All right. If we do if power of a power, we said if you have a, well, I know I use either a or b. The book says b, but I'm gonna use a. So if I have a power m power n power of a power, we're gonna multiply the exponent. If you see a over b power n, give each of them their own exponents, because the bases are definitely different. So if it's different, then you cannot do that. If you see a times b power n, give each of them their own exponents. Remember, those are properties. If you see a power negative n, then you flip it and make the exponents positive. Okay? So I'm hoping you can see that the same. If it's negative in the denominator, certainly you can do it in the numerator. All right, let's try to do all of this. We're gonna try to go over that examples. When we simplify, we're gonna have give each of them their own exponent, 2 power 4, x power 3 power 4, y power 6 power 4. 2 power 4, 2 times 2 times 2, that gives you 16. A power of a power, we need to multiply. 3 times 4 is 12. Y power was, please? Thank you, 24, because we multiply the exponent. Now, there is a technique when the exponent is negative. If the exponents for both terms in a quotient world is negative, you can flip the inside first. So what we can do, flip the inside and you raise it to a positive exponent. Yeah, I know, but you can do it step by step. But you know, if I want to make this one positive, the exponent positive, I flip the content, the terms inside of the parentheses. So we're gonna have y power 4 power 2, 5x power 2. So y power 8 over 5 power 2 times x power 2. Y power 8 over 25x squared. Okay? Is that a good thing? Good, bad? All right. We covered a lot of these expressions. Of course, I'm gonna have a chance to do more. I could even go in and set a slide right there. Let's set this, because I know some of you might need more practice. If we ask you to simplify, let's go for examples with negative 6x to the second y to the fifth times 3xy cubed. Now combine like terms, we're gonna have negative 6 times 3. That's the like terms. And we're gonna have x second times x. We're gonna have y power 5 times y power 3. With that, negative 18. Okay, we're gonna have x. Remember there is a 1 here. 2 plus 1 is 3. Y 5 plus 3 is 8. Feel free to review everything again. Make sure you get it correct. Now, that's an example, but what if you have a second example where it says 100x to the 12 power y power 2, 20x 16 y power negative 4. All you need to do for these examples, first of all, 100 divided by 20, remember, 100 divided by 20 times x to the 12 divided by x to the 16 times y power 2 over y power negative 4. So 100 divided by 20, I believe it's 5. X power 12 minus 16 times y power 2 minus negative 4. It gives you 5x power negative 4 times y power 6. I skip one step because I don't need to say 2 plus 4, 2 negative give positive. I'm hoping you can see it, because when you simplify, you need to keep it with positive exponents. We're going to flip the x power negative 4 to the bottom. So we're going to have 5y power 6 over x power 4 and make all the exponents positive. Okay? Well, I wanted to go over these examples first before we start talking about something that is very important, that we call scientific notation, right? You know, Earth is about 4.5 billion years old, well, of rock orbit the sun, right? Because a billion is 10 power 9, the age of the world is years, is very difficult to write by using 0.00000. So instead, for billions, we can replace it by 10 power 9 if you see billions, right? And whenever you write an expressions in the form a times 10 power n, so you call this one scientific notation. But remember, a is greater than or equal to 1, okay? But a cannot be 2 digits, right? And it cannot be less than 1, okay? So a can be 1, 2, 3, 4, 5, 6, 7, 8, 9. It can be 1 point something, 2 point something, okay? Can be 9 point something, but never 10 point something, 20 point something, all right? So that's only 1 digit and decimal for that, all right? And n is an integer. Exponents can be positive or negative, but not a decimal or something, okay? It should be an integer. Now, if you understand this, if they ask you to rewrite these expressions, using scientific notation, remember, all you need to do, just plug 9 digits after the decimal point. So we have -2 because we have 9, right? If you have 9 digits, consider the 6th one of them because it's after the decimal point. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's power 10. And you know what to do. Put some comma and make sure you got it. Okay? So it is when the exponent positive, you added, you move from left to right when the exponent is positive because you're going to have a big giant number, all right? Well, in this case, because it's negative right there, so we cannot say it's a big giant number, but at that point, it's in terms of whole numbers. But the second one, because the exponent is negative, we're going to move from right to left. So what we're gonna do, first of all, I'm gonna write there 3, 0, 1, 7. So we're going to move from the 3 because the 3 is where we have the decimal point. So the 3 is 1, 2, 3, 4, 5, and 6. So that's where I have my decimal point because we said power 6. So this is the power 6. 6 digit. Okay. So that's why you see we have 5 zeros and the 3. So that make it 6 digit. Sounds good? Okay. Look at the blue one. Here they give us the first one. They give us a scientific notation and ask us to express it in decimal notation. Now they give us the decimal notation and ask us to rewrite it in scientific notation. First of all, you need to remember to use the rules. Okay, the property. A cannot be 2-digit. You cannot say 5,210 times, or you cannot say 521 times. You cannot say 50.1, but it must be only 1 digit. So we're gonna do 5.21 times 10 power. Let's say power. Start where you said 5 point. Point is 5, so we're gonna do 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means it's power 9. Okay? Does that make sense? You okay with that? Okay, 10 power 9. Look at the second one. We can continue to do as many as possible as long as you get it, you understand it. It says, I'm gonna go with, remember the decimal point must be only 1 digit here, 8, 9, 3. Now from that point right here, count to the left. How many digits? We have 1, 2, 3, 4, 5, 6, 7, 8. Okay, and because we move and make it decimal, it's gonna be 10 power -8, not +8. So when you move from left to right, exponent, because the exponent is positive, if you move from right to left, the exponent is negative. We're gonna see just some reviews and certainly things you already understand. If we ask you to simplify expressions, if they have the same base, you must add the exponent. So that would be -5 plus 10 is 5. You see for this one, the same base. First of all, I pay attention to the same base. So 7 plus 0 is x power 7. This one, again, x power 11 plus 5, x power 16. We can go with some other examples right there. For example, we multiply the exponents. So 11 times 5, because power of a power, we need to multiply the exponent, right? -5 times 3. X power -15, but you can still rewrite it as 1 over x power 15 and make it positive. Okay. When you have quotients, we said pay attention for the bases. If the bases are the same, we subtract the exponent. Right? X power 14 minus -7. X power 14 plus 7. X power 21. When we have bases the same product, so we can multiply these two. We have -2 times -9. See, -2 times -9, and we have x3 times x6, y times y4. If we negate 2 negative, give you positive 18. X power 3 plus 6 is 9. Y1 plus 4 is 5. Questions? There is one problem that I would like you to try on your own. I don't know if it's something you can be doing or if you want me to do it with you, because in this problem, it stated the United States government spent more than it had collected in tax, resulting in a budget deficit of $984 billion. So express this number in terms of scientific notation. First of all, remember, for scientific notation, you must have only 2 digits, so 1 digit. So I'm gonna say 9.84 because they said $84 billion. Okay, $984 billion. That means this number right there, remember, billions is power 10. It's like you have 984 times 10 power 9 because they said billions. Or if you want to write it in terms of billions, this is how you're going to write it. 984 billions, 90, right? 0, 0, 0, 0, 0, 0, 0, 0. So that's 9 billions. Now let's count from here to the right how many digits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So our answer is 9.84 times 10 power 11. Okay, got it? There are approximately 32,000 seconds in a year. Write this this number in scientific notation. 32 million, sorry, 232 million. So for B, as you see, 32 billions. First of all, remember it should be only 3.2. So if you go here, count the rest of the digits. How many you see after the 3? Yes, 7. So that should be 10 power 7, positive. Okay. Use the answer from A and B to determine approximately how many years is 900. They said in a year there are 32,000. So if you want to know how many in 9,000, because 984 billion seconds. So in a year. So determine approximately how many years. Then you need just to do the 984 billions with the zeros. And you divide it by 32 billions. 32 millions. And approximately the answer would be 30,750 years. Right? I know some of you need explanation on radical and rational exponents. In a different video, I would come back to cover this with you. In the meantime, you let me know if you have any questions. Take care.